Usually it says really loud. This meeting is being recorded. I think my volumes are screwed up around here. All right. Oftentimes you'll hear people call this U substitution just because the letter U is often used and it gets conflated together. But the idea is just substitution. All right. So we're going to start off with a real quick example. This is a dumb thing that will strike you as being a dumb thing to say, but it is true. Here's one of my favorite integrals, right? How many of you have a favorite integral? Nice. What is your favorite integral?
The integral of e to the x.
Oh, there we go. E to the x. That's a good one. All right. So here we go. Here's my example. What is the integral of sine of x times cosine of x times dx? All right. I mean, don't say it right away, but what integration technique do we need to integrate this? That's right. I don't know, sir, but I'm going to guess substitution, right? So yeah, substitution. So what could I set as my u? Cosine of x? That works, cosine? One of the reasons I like this one so much is that I can choose cosine or sine. It actually doesn't matter. It's one of the things that I like about this integral. And now that you've said cosine, I'm going to tell you, and now that you said cosine and I told you it doesn't matter, I'm going to say, let's actually choose sine, all right? And then can anybody discern why I prefer sine?
You don't want the negative?
Right, when I do du is just cosine x dx. I can avoid the minus sign. Does that make sense to everybody? And I will tell you, it's a conversation for a different day, and I think it might be an example in the book about why it doesn't matter which one you pick. The minus sign will work out in the end, but for the purposes of what I want to do right now, I don't want to mess with that minus sign. So I can come here, and then this section is focused on substitution and definite integration. When you learned substitution last semester, you learned substitution with indefinite integration. You never put bounds on your integral. Okay, we're going to focus on that. That's going to entail us reviewing substitution in general, right? So right here, I can see that I have this is the same thing as du, and I can see that this thing is the same thing as u, right? So that's all part of substitution. So I make my substitution, and I have the integral of u du. Everyone good? What's the antiderivative of u? All right, with respect to u, that is 1/2 u squared, or u squared over 2. And then I can tack on a plus c because this is an indefinite integral. And then I'm going to substitute back and get a 1/2, what? I'm going to use this way, sine of x squared plus c, right? Or I could write this as 1/2 and just to use that trig notation, 1/2 sine squared x plus c. All right. Everyone okay with this so far? Yes.
Can you remind me of so last semester they had there was a set of steps that had names. It was like sub, resub.
Oh.
Do you know those by chance?
I don't know those actually. That might have been a particular teaching technique of your instructor. Who did you have for talk last year?
The department head.
Seamers. Oh, I'm sorry. That must have been a terrible experience. I'm way better than he is. So now I have to talk to him and see what he does with that. I don't know. And then you folks on Zoom, I think the audio in the room might be turned off in a way that I don't know offhand how to turn back on quick. I'm not going to worry about it too much, but if you have a question, throw something in chat, okay? And that'll pop up for me. All right, now let's do a definite integral. All right, so now there's steps involved, and then, well, I'll show you. What if I wanted to integrate from 0 to pi over 2 of sine of x cosine of x dx, right? Here is the method that you want to do. And this method is not wrong. But I also want to show you a new method, okay? And the new method, once you have confidence with the new method's faster. But the old method, you're going to feel more confident in, and you're always want to fall back on that. So I'm going to try to push you into the new method just to say, this is what you can do, and it's better, but you just don't trust it as much, all right? So what if I were you, and I'm learning this for the first time, and I see this definite integral, what my first thought would be is, well, this is just equal to, right? Well, not equal, arrow, right? Well, what I'm going to do first is just think about this, right? Oops, cosine x dx. I'm going to think about the indefinite integral. Oh my word, what did I do? Sine x and cosine psi. Just got to start over. There we go. Sine of x cosine of x dx. Right? And then we know that that antiderivative leads me to a 1/2 sine squared x plus c, and then that's going to lead me to a 1/2 sine squared x evaluated from 0 to pi over 2. Is everyone okay with that logic? And if I didn't teach you anything about how to do definite integration by substitution, that's what you would do. And again, I think I preface it, it's not wrong. That'll work for sure, right? So your intuition, there's times where I'll tell you, this is your intuition and your intuition's not right, but I got to get it out there before we move on. In this case, your intuition is right. This is what you can do. And then I'll finish it up with, well, this is 1/2 sine, and I want to do is this, put a parentheses around this, 1/2 pi over 2 squared minus 1/2 parentheses sine of 0 squared, right? And when this is all done, what sine of pi over 2 is what? 1. And so 1/2 times 1 squared minus, what's sine of 0? 0. This is just 1/2. And I could change some colors here, I guess. Put a dark green. This part's equal to 1. This part's equal to 0. And we get 1/2. But then here is the observation to make. Look at what's in those parentheses. Inside this parentheses is sine of pi over 2. That's my upper bound, right? The sine is what my u is equal to. And pi over 2 is my upper bound. Over here, I have sine of 0. Sine again is my u. My 0 is my what? Lower bound, right? And effectively, what I have is a 1/2 u squared minus a 1/2 u squared for different values of u, if you will, right? There was a time where my integration was just 1/2 u squared before I substituted back. So what I did is I started off with x, switched over to u, integrated, switched back to x, and then evaluated x stuff, right? Again, not wrong. But what I can show you is I can start with x, switch over to u, and get a final answer. Not switch back to x stuff again. Okay. So what I'm going to do is, let's just notice what's inside here. This is just, again, sine, my u function, evaluating the bounds, upper bound, minus the u function evaluating the lower bound. So now I'm going to say next page, new method. All right, so next page. We're going to go back to blue, I suppose, and say the integral from 0 to pi over 2 of sine of x cosine of x dx. I'm going to set up my substitution. I'm going to say again, u is sine of x, du is cosine of x dx. And now here's the new thing. I'm going to evaluate each of my bounds, I'm going to evaluate this function here at each of my bounds. So u of pi over 2 is the same thing as sine of pi over 2. And we've already established that sine of pi over 2 is 1. And then u of 0, that's a u, is the same thing as sine of 0, which we reminded ourselves is 0. And then in red here, this is my new upper bound. And this is my new lower bound. Everyone okay with that? Now, I'm going to say it once here, and it might show up again sometime. This is not the upper bound because it's bigger. This is the upper bound because it came from the old upper bound. I don't care which one's bigger or smaller. It's just the old upper bound was pi over 2, so this is the new upper bound. Old lower bound was 0, so this is the new lower bound. There are cases where this number here is smaller than this number here, and it feels weird putting them in the opposite and natural place, and that's just what you do. Okay, so now I can say, I'll do all the substitutions. This is equal to, I want blue again. This is equal to the integral from 0 to 1 of, wow, u du, right? And that's 1/2 u squared evaluated from 0 to 1. And then I can see that's just 1/2. It's not amazingly faster, but it is faster. True? Everyone okay with this? Anybody have questions? Folks on Zoom, you have questions for me?
So this was just an easier way of clarifying. Instead of having just the pi over 2, it's easier to simplify it with 1 instead.
Parker, are you talking? So your mic went off. I don't have volume in here at the moment. Try this real quick. Try talking again.
My question just was, is it just replacing the pi over 2 with the 1 so it simplifies it easier?
Right. Well, it's not so much that 1 is easier to work with than pi over 2. Rather, what it is just the fact that I have gone from x to u to final answer, not x to u back to x to final answer. I've skipped one extra resubstitution step. Does that make sense? So now, just out of curiosity, I told you it didn't really matter which one I used for you. Let's go ahead and flip around and use the other, I'll say once again. We'll do this quickly. What if we had set u to cosine like was first suggested to us? Just to see, right?
So I have a quick question.
Sure, go ahead.
What is du then? Like, is it just not relevant to the?
What is du here?
Yeah, like, do we just ignore it because isn't it cosine?
Yeah, this is one of these things that gets students all the time. And it's kind of this weird thing that once you get past it, you're past it. But until then, it's like, it's just a weird quirk about math. I'll throw back a question to you. What happened to the dx here? And the answer is it just goes away because of integration, right? But now when I go over here and I have a du and I'm integrating with respect to u, the question is, what happens to the du? Just like before, it just goes away. It's part of the integration step. Does that make sense?
Yes, sir. Thank you.
Okay, yeah. And don't take my words as being like a criticism or whatever. I get that every semester, and I was thinking before class, like, I wonder who's going to ask that question today. I mean, it comes up all the time. And so the du goes away just like the dx goes away. It's part of the integration step. All right. So one more time, integral from 0 to pi over 2 of sine x cosine x dx. U this time is cosine x. That's what you told me you could do. That makes du what? Negative sine x, right? Everyone all right with that? Now, there are two main ways that you can handle this. How do I get a negative sine x? Some people will put a minus sign up front and a minus sign inside here, and two minuses cancel out. That's all fine. Over the years, as I teach the stuff, I've gone back and forth, and I've kind of settled on, this is what I'm going to show you to do, is I'm going to say that I can see there's a sine x, and again, these are all multiplied together. There is a sine x times a dx here, right? That exists already. So what I'm going to do over here is say negative du is equal to sine x dx. So over here, I'm going to replace the sine x dx with a negative du. Does that make sense? And then this part here is going to be my u. This part here is negative du. Are those substitution steps making sense? All right, now then here's the kicker. What are my new bounds? U of pi over 2. What is cosine of pi over 2? It is 0. What is cosine of 0? 1. Oh. So all of this is going to combine together to give me an integral. What's my new lower bound? 1. New upper bound is 0. Feels weird, right? Because my old lower bound led to 1, my new lower bound is 1. And now my integral, I'm going to put it in sort of order. This is u times negative du, right? All right, and then this is the same thing as negative, the integral from 1 to 0 of u du, right? And now what do I want to do? Yeah, let's just go ahead and flip the bounds, right? 0 to 1, and now I'm back where I was before. I get 1/2. That's not the example I wanted to start with, but I don't mind making that the number 2 example, right? Just that substitution. So again, that was not the wrong way of doing it. It was just a matter of, I wanted to avoid the minus sign the first time around. Questions from anybody? All right, let's do another example. I have, let's see here, integral, new example, brand new, no more sines and cosines this time. Integral from 0 to 1 of 1 over 2x plus 3 dx. Okay, so a suggestion for what I can use for my substitution here. Okay, so yeah, not a whole lot of choices to choose from. So u is equal to 2x plus 3. That makes du equal to what? Close to dx. There we go. As math teachers can be kind of pedantic about this, but the dx is important. It is multiplied. That's one way the x goes away over here when I do the substitution. Right?
Wait, sir, I completely missed that step. What?
From here to here?
Or for why is it 2x plus 3?
Well, it isn't exactly clear that that's the thing to do per se, without looking ahead. And I can see that if I did that, that would become 1 over u, right? If I can make that substitution, and I know how to integrate 1 over u, or I know how to integrate 1 over x. Is that a fair statement? Okay, and so then I'm shooting for that. And then the question, my train of thought is usually, oh, if I can make this thing u, I can integrate 1 over u. So let's try that. U is 2x plus 3, du is 2x. And then I look at this and say, can I handle this? Or did I make a mistake somehow? All right, does it somehow not work? And in this case, this works just fine. I can handle this. And what I would do is say, well, I see a dx. I don't see a 2dx. And again, there's ways of handling this. The way that I handle it is to say, well, 1/2 du is the same thing as dx. And so then this portion right here turns into 1/2 du. And then this stuff in here turns into just u, right? I can make those substitutions. And if I can make those substitutions and all my x stuff goes away and I only have u stuff left, then I have likely substituted correctly. If I am left with u and x stuff in the same integral, then I've messed something up where I haven't done things correctly. I can't integrate that case. Does that help, Linda?
Yes, sir. Thank you.
Yeah. All right, and then there's still another step I want to do here. I want to change my bounds. New upper bound. Looks like it's going to be 5. And my new lower bound looks to be 3. Yep.
So when you said that it's 1/2 du, if you were to rewrite that integral, it's the integral from 0 to 1, u 1/2 du, like you just straight up write.
So my new integral is going to be the integral not from 0 to 1, but from 3 to 5, right?
But yeah, I meant that, but when you're solving for u and then du, you just like put them together, even though that you now altered du and you made it constant.
So inherent in all of this is the fact that this is being multiplied, right?
Yeah.
So it looks really weird, but that is the same thing. And you will see this in some other like printed calc text. You'll see things written like this. Even though it looks weird, right? And then that's the same thing as this. And that just looks wrong, right? But it's just being multiplied together, right? So when I have this, that is just du being multiplied by 1/2. And that's all it is, right? So I can write this as 1 over u times 1/2 times du. And that's just a fine statement to make. Does that help? Is that addressing your question? Okay, yeah. So the beginning of the semester, and I said something, and when I say things once, I don't expect that I just have to say it one time and everyone remembers, right? This is not a bookend, it's being multiplied through. And I went through all of my undergrad treating it like a bookend. It was just this thing that hung on the end. And every once in a while it magically disappeared and all that kind of stuff. And somewhere in grad school, it like clicked, oh wait, this thing's being multiplied. And if I treat it as though it's being multiplied and not a bookend, life actually just gets a lot simpler. And so I kind of harp on that too, so that you have a better understanding than I had at your age. Back when I was your age. That's my old man voice, just to let you know, right? So. All right, now you can handle this 1/2 in a variety of ways. It is easy just to pull it out. And again, the reason I can pull it out in some sense is that this integral symbol is a summation. And this says sum up a bunch of things and multiply all those things by 1/2. Well, I'll just pull it out and I'll sum a bunch of things and then multiply them all by 1/2 effectively. Now, what's the antiderivative of 1 over u? Right, natural log. And then technically it's the absolute value of u. And then we can drop those absolute value signs here because both of these numbers are positive, right? This is going to lead me to 1/2 the natural log of, I'll put it in parentheses, natural log of 5 minus the natural log of 3. And at the moment, I don't particularly care what that number really is. That's just our answer. Questions about this example? What can I review? Yep.
So could you do an example where you have negative bounds and you still have element of absolute values, you just get rid of the negatives and treat it like an absolute value problem?
Yeah, well, so yeah, if I had, it's 2x plus 3, I gotta make sure that I don't, well, I can just go from like say -10 to -8, right? Of 1 over 2x plus 3 dx. That's going to be the same thing as 1/2 the integral of 1 over u du. And then my bounds are what? 2 times -8 plus 3 is what, -13. And then 2 times -10 plus 3 is that -17? This goes from -17 to -13, right? And so then this thing here, I could go through my steps. I can see what's coming. It's going to be 1/2 the natural log of the absolute value of -13 minus the natural log of the absolute value of -17. And then I can make that 1/2 the natural log of 13 minus the natural log of 17. Does that help?
Yes.
Now, is that a positive or negative number right there? So the natural log function is an increasing function. It looks like this. So the farther out you go, the bigger it gets. So the natural log of 17 is bigger than the natural log of 13. So I'm going to get a negative number when it's all said and done. But the fact is that this function right here, oh, shucks. There's no like undo function, I don't think, is there? There is. This function here looks like -1/2 is where I have a vertical asymptote. Something like this. So in this integral here, I'm asking about negative area under the curve. I'm asking about something under the curve over here, which is why I end up getting a negative number. This is less than 0. Everyone all right with that? This second example is just a bit of an aside, but it's fine. All right, let's do another example. Completely unlike the first or the second. Oh, I got 2 good ones. Which one should I do first? This is a good one for us here. Integral from 0 to 2 of 1 over x squared minus 2x plus 5 dx. That's a good one. Do we have any ideas what we need to do for this?
U could equal x squared.
Okay, so here is, I will tell you before we get too far into it, this is not going to work out well. But let's go ahead and see what happens when I try something that doesn't work, right? What happens if I say u is equal to x squared, then du is equal to 2x times dx, right? Then I say, oh, I have, this could be a u. But frankly, I'm not necessarily sure how to handle a negative 2x because this negative 2x is not being multiplied by dx. The 1 over x squared minus 2x plus 5 is being multiplied by dx, right? I don't have this here to substitute. And if I try my trick like 1 over 2x du is equal to dx, then I still have trouble because I make the substitution and now I have x stuff over here. I'm still not sure how to get rid of that. It feels like a bit of a mess, right? I'm not liking that one. But I don't mind us trying because this kind of ties into Linda's question from a while back, which is, how do I know this is right? Well, sometimes I know it's right because it never went wrong. When I tried this one, I tried it, and it wasn't the end of the world that I tried something that failed, right? Oh, well, I'll try something different. All right, yeah, go ahead.
Change up the format and the way you express the exponents. So when the x squared is the choice to the top by turning it into x to the negative second and 2x to the negative first.
I can't do that either. So here's for you folks on Zoom, the essential question is, could I rewrite this? Here's a new, if you don't mind me saying, bad idea, right? Is to say, is this the same thing as x to the negative 2 times or minus negative, or sorry, 2x to the negative 1 plus 5 to the negative 1? Is that the same thing? And so then effectively what you're saying is 1 over 3 plus 5 is the same thing as 3 to the negative 1 plus 5 to the negative 1, right? But what you're saying there is 1/8 is the same thing as 1/3 plus 1/5. Oh wait, that's not true, right? All right, so all that also doesn't work. Ellie, I see your hand. What's up?
Yeah, could you split it into 3 fractions?
So that kind of ties into this one. Is 1 plus over 3 plus 5 the same thing as 1/3 plus 1/5? Is that the same thing?
Oh, that's what you're saying. Okay.
Right, yeah, so I can't split this up into 1 over x squared minus 1 over 2x plus 1 over 5, right? And these are all things, and the problem that we're having is that I just did an example where I had this fraction and I got the natural log, and it turns out natural log is not going to appear here at all. We're trying to head down the wrong path, trying to force things into it. Yeah.
You need long division.
I don't need to do long division, but you're getting warmer in that the answer is a 3-word term. It's one of our favorite 3-word mathematical terms. When you got up this morning, you probably said, hey, look, it's snow. That's cool. The only thing that can make this day better is if we complete the square in calculus today. Is that what you said? Really? Man, we had totally different experiences this morning. So I'm guessing that the complete the square part was true. You were disappointed about the snow? Is that what it was? We need to complete the square. Do you remember how to do that? That's what I expected you to say. All right, perfect. Let's remind ourselves how to complete the square. I'm just going to write over top of that one over there. Completing the square maintains equality, but I just changed the form. It just looks different, but it's the same thing. So the idea is I want to have a leading coefficient of 1, but I'm going to be thinking about it as x squared plus bx plus c. And so what we're going to do is take half of the b value. So what I have is x squared minus 2x, and I'm going to give myself some space, plus 5. So this is my b value right here, -2. What's half of my b value? What's that? -1, right? Half of the b value is -1. And now I'm going to square that. I get +1, and I'm going to add and subtract that number in. +1, -1. So take half of b to half of b squared, and then add and subtract. So by adding 1 and subtracting 1, I have not changed the value of this expression, correct? I have added 0 to it. But I am going to change its form. And the reason that we chose this quirky, take half of it and square it, add and subtract it in, that is specifically designed so that I can write this as what? It's something squared. X minus 1 squared. It's that half the b value is right here. And then, of course, this is just a number. This is a +4. Are we okay with that? So my original integral turns into the integral from 0 to 2 of 1 over the quantity x minus 1 squared plus 4 dx. And now the question is, do you remember how to handle this? This is similar to one that I asked in the test. Do you remember how to handle 1 over x squared plus 1? Inverse or arctangent, right? So I am going to share the calc book with you real quick. And then end of the book kind of stuff. Index. Is it after the index or is it? Here we go. Your integration rules. Right there, number 22. The reason this rule works is because of substitution. So I have this kind of thing mostly, and I'm going to get this thing out, hopefully. Okay? So now I'm going to go back to the whiteboard. And say now it's time for a substitution. I'm going to say u is equal to x minus 1. That means du is what? 1 dx, yeah. And that's a really simple substitution, right? Old upper bound was 2. New upper bound is 1. Old lower bound was 0. New lower bound is -1. And so this becomes the integral from -1 to 1 of 1 over u squared plus 4 du. And we're going to look at that formula. That formula says that when you have an a squared in your denominator, then the a comes out. So I specifically chose this example to have a 4 down there, right? Because that is what squared? 2. So 1/2 is going to come out, or 2 is going to come out. this is going to lead me to 1/2 arctangent of u/2 evaluated from -1 to 1. Everyone all right with that? And then this becomes 1/2 arctangent of 1/2 minus 1/2. I didn't really want to put that line there. Arctangent of -1/2. And the properties of arctangent say that we could simplify this. This arctangent of -1/2 is just the opposite of the arctangent of 1/2. Since they have opposite values and I'm subtracting, it's going to end up just doubling it. My final answer is the arctangent of 1/2, which I don't know what that is. Oh, it's not necessarily a nice number. You could leave your final answer like this and then get a numerical approximation. That's fine. So we did a substitution, but we also, one of the big reasons I did this was because I wanted to practice completing the square. And in fact, technically there was 2 substitutions that happened here. We did this substitution to get to this point, and then that rule uses another substitution to get to this point here, and we just sort of, in the book, and if you read through it, they'll justify where that comes from. We're going to just use that as a formula that we know. Good. Questions?
Wait, where do we get tangent?
Where did we get arctangent?
So in the integral from -1/1, you don't have the tangent there, and then there's a tangent that appears.
Yeah, the audio is not the best in here, but is the question, how do I get from here to here? Is that the question?
Yeah.
Okay, so we will look in the back of the book. The back of the book says 1/x² plus a² turns into 1/a arctangent of x/a. And in our case, this was actually u², and that's okay, I can make that substitution. And this was 4. And so if that was 4, this becomes 1/2 and u/2. Does that help?
Yeah. Sorry.
It's good? Okay. Other questions? Yes.
I kind of zoned out when you do the square. So I'm probably gonna have to contact Academy that later, but.
All right. Or you could watch the video that I posted, which is probably better than Khan Academy.
That's very good. Can we just do one more example independent of maybe completing square?
I appreciate your frankness. It starts with, I stopped paying attention. Do you mind teaching that part again? Elliot, you had a quick question?
Yeah, so this is like ideal situation, right, that it like fit into one of the trig rules.
Right.
Because like the completed square doesn't always work out like that, right?
Right. So, right. We are going to get to, so the question is, okay, that little quadratic, I can complete the square on it. It worked out nicely, right? What would happen if I completed the square and I had like an x minus 1 squared minus 4? That has a different form, right? What do I do with that? And so section 6.5, which we're going to get to in probably about 2 weeks or whatever, is something called partial fraction decomposition, we'll talk about how to handle that case in a while. So one thing that I haven't done, in the short answer is we're about out of time, so we're not going to do another complete the square. One thing that I didn't do well here is set up what we're doing in class right now, basically. We learned about the definite integral. Chapter 6 is all about techniques of integration. You learned about the basic principle of antiderivatives last semester. We've talked more about finding definite integrals so far, just the basic principle. Chapter 6 is all about getting a toolbox of different techniques to handle different kinds of integrals. A huge tool, a huge hammer in your toolbox is substitution. It's what you reach for a lot, is that hammer. Substitution covers a lot of stuff. And then another one we're going to cover next time in class is integration by parts. It's like a handy, trusted Phillips screwdriver. I'm going to grab that a lot too. But then there's some pliers, and there's going to be some other stuff that we're going to use along the way that fills out this toolbox to answer some stuff. So put a little pin in that one, Ellie, and we're going to come back to it in a while. All right, and then as far as completing the square, go back and watch the video here. Yeah, I told you you can Khan Academy it.